Alright guys, welcome back to another video on electrophilic aromatic substitution. So we covered all the basics reactions. We covered activating groups, deactivating groups, ortho-para directors, meta directors, right? And we covered the Birch reduction and the oxidation reactions. One other thing I do want to go over for electrophilic aromatic substitution is when we react it with an anhydride, when we react benzenes with anhydrides. So what is an anhydride? So it would be this sort of functional group. All right, so we have these essentially, it's like a shared ester. You guys can think about it. All right, so we have this oxygen connected to two carbonyls, and we can have these as R groups. They're just carbon chains. And so we're going to react these guys with benzene. All right, so this is a good reaction you should know. It could be very useful in a synthesis. All right, so how does this work? So we're going to start off with a very simple example of an anhydride, and we're just going to use methyl substituents. All right, so let's get started. So here's our benzene. And again, we know we can have some sort of substituent like OCH3 on here, but we're just going to keep it simple for this video. All right, and we're going to react it with our anhydride. So it's going to look like this. All right, just methyls, and let me just make this a little bit better. And so what we do is we put it over AlCl3. So similar to when we're doing our Friedel-Crafts reactions. All right, so what is the mechanism for this guy? So here's the first step. Remember, usually when we have this AlCl3, what happens is this reacts with our Lewis acid first, right? Remember, a Lewis acid is something that accepts a lone pair. So here's our aluminum, Cl, Cl, and Cl. So first step is the oxygen of one of these carbonyls is going to attack this aluminum. Remember, there are two lone pairs here, all right? I know this is a little bit odd to see, but you will see this in a lot of reactions in Orgo2, especially when we get to maybe like stuff like acetals. You'll see oxygen's part of carbonyls that are going to be protonated, stuff like that. All right, so what this is going to do is it's going to create an intermediate that looks like this. Aluminum gets a negative, oxygen gets a positive. All right, now these arrows are going to be a little bit confusing, so we'll take it step by step. What happens is the lone pairs on the carbonyl oxygen that is not participating in this new bond to the other one, they're going to come down. All right, now to preserve the octet rule, we're going to have to break this bond or this bond. Now, we're not going to break a carbon bond, carbon-carbon bond, so what's going to happen is we're going to use this guy. So what we're going to do is this bond swings out and is going to come around over there. So this is going to form a double bond right here. But again, we need to keep the octet rule. So we're going to have to resonate this double bond up. So that comes up over here. So what we now get, if we focus on this part, so what we did is we broke this bond right here and resonated a lone pair down, forming a triple bond. So what do we get? We get this. And I'll write in the CH3 here. And we have a positive charge on that oxygen. Remember, this is that acylium ion. All right. Plus, let's look at what happens to this side. So we're going to get, let's see, this bond broken, a double bond here, and this became a single bond. So oxygen, right, draw this. Here's the other oxygen, down to AlCl3, still a negative here. The new double bond we formed, and here's where that old double bond used to be, and we resonated that up. All right, so that's why the positive charge went away on this guy. All right, so now we have this acylium ion. What we're going to have to do now is we're going to react it with our benzene. So the benzene, it's going to use one of its bonds, attacks that carbon. So this carbon, remember there are two carbons in this compound right now. One of these bonds resonates up. and we get this intermediate. So these two bonds stay the same, we didn't touch them, all right? 2-carbon compound, and remember, one of these bonds, we have a triple bond resonated up, so we're left with a double bond. All right, remember we had a hydrogen here. All benzenes have hydrogens on the carbons unless there's some other substituent shown. And we have a positive charge here. Now what's going to happen is all we got to do is restore the aromaticity. So you can just either go like this to show something is that single bond is using those electrons to form that pi bond. Or what we're going to do if we want to be more precise is go back to this intermediate and show that this bond reaches out and grabs the hydrogen. Draw that better. And then this bond collapses. So what do we get as our products? Here's our benzene, and we added this ketone. Plus, so what we showed here is that bond disconnected from AlCl3, stayed connected to the oxygen and grabbed the hydrogen. And we still have the rest of this compound. So we're going to have this. Oh, my bad. Here's this H. And if we just wanted to redraw it so it could look a little bit more familiar, all we have is this carboxylic acid, and we regenerated our AlCl3, so it can be used again. So this is going to be your product, all right? So you can see if you want to do the shortcut, what you should just pretty much do is look at the anhydride, pick one of the sides, right? And what you want to do is pick a side to the left of the central oxygen or to the right. So I'm going to pick, let's say, this side, draw a line, and cut out the rest of it. And just attach that portion to your benzene. So we'll have this. All right, if you want me to like color code this, so here's our ketone, draw it in blue. So it's going to be this part. But cut this out. All right, so we'll just split this right down there. All right, and so we can do this with other anhydrides, so we can do this with some anhydrides like this. Now, when you want to do this, you want to keep the anhydride symmetrical. Otherwise, you could maybe get a mixture of products. All right, because then it'll be a little bit harder to differentiate between for the reaction to differentiate between attaching this end or this end. All right. So if you're doing this in the synthesis, you may have a problem when we have this sort of mixed anhydride. Right. So that's how we did these open chain anhydrides. What if we did anhydrides that aren't open chains? So what exactly does that look like? What am I talking about here? Well, talking about this sort of an anhydride. These cyclic anhydrides. Now the reaction is going to be exactly the same. The mechanism works identical. Put this over AlCl3. Now also don't get caught up. We can use this with different kinds of ring structures. In exam 1 of the spring 2019, this was one of the anhydrides that was used. 4-membered ring. All right, so you can do 4-member rings, 5-member rings. All right, you can be pretty creative. Now, you could have done that synthesis without using that cyclic anhydride. It was definitely possible, but it could be more steps, you know. So, and you might have to think a little bit more outside the box to do that. But there are ways to get around certain things in synthesis. But this is definitely a reaction that you guys should know. So how do we do this with the cyclic anhydride? Well, like I said, the mechanism is going to be identical. So what's going to happen is, let me redraw that. Here's our anhydride. Here's the Lewis acid, AlCl3. So this oxygen of the carbonyl attacks the aluminum, and we get this intermediate. So it's going to be bound to the aluminum, Cl3, negative charge, positive charge. Now what happens is, remember, the carbonyl that is not participating in that bond to AlCl3, it's got those two lone pairs, and it's going to bring one of them down. This comes down. This bond here is now going to have to break, and it's going to go and form a double bond this way. And to preserve the octet rule, we're resonating this guy up. So what does that do? It's going to give us this weird looking intermediate. Now I'm going to try to draw it in a way that will make it easier to see how I'm breaking the bonds. Here's our triple bond, and now I'm going to do a little bit, I'm going to draw a bent line off of a triple bond. Obviously this is not how you should do it, but it's just to help you guys visualize it. So we're going to have bonds like this right now. So remember, we had a bond like this. That bond broke. All right. We have our new double bond to that oxygen. So remember, this is the oxygen that was connected to that carbon. All right. We now have a single bond here. AlCl3. That still has a negative charge. All right. And remember, this oxygen now gets a positive charge. So this is our intermediate. If we wanted to draw it properly, remember, because triple bonds should never have bent lines coming out of it, all I'm going to do is do this. So here's that carbon. All right. So here is one of our intermediates. So you see, in a cyclic anhydride, we kept all this. When we had our linear anhydride, something like this, or our open chain, right, we ended up kind of like cutting off that half of the molecule. In this case, we did break that bond, but because there was still these bonds, it's not fully cut off. So now we take our benzene. One of these double bonds comes in and attacks that carbon, resonates this up. So now what's going to happen is we have a bond to this carbonyl group. We're going to have a hydrogen here, plus charge here, and now let's count our carbons. Remember, it can never be too safe. 1. Don't forget this carbon of the triple bond. That's 1, 2, 3, 4. And let's count our original thing to make sure. 1, 2, 3, 4. Good. We have 1 right now. That's 2. That's 3. And that's 4. Now on our fourth carbon, we had a carbonyl. Let me draw that 4. Oxygen down to AlCl3 minus. All right. So now what we have to do is restore the aromaticity. So what we're going to do is we're going to take this bond and we're going to deprotonate that H. So this bond is going to, what this symbolizes is it's going to disconnect from the aluminum, stay connected to the oxygen, grabs that H, and then this bond collapses downward. So our final product is going to be this. Benzene. That carbonyl. And now what's going to happen is this O grabbed the hydrogen and we regenerated our AlCl3. So you see, we created a carboxylic acid. All right. So this is an extremely useful reaction. All right. So it can definitely help you on a synthesis. All right. So I would make sure you guys know this sort of mechanism. It can really help you out over here. Right. And so it can be useful in a lot of synthesis, like I just said, and it could come up in maybe some sort of multiple choice or stepwise problem. All right. Now, one other reaction before we close this out that I want to cover is going to be SOCl2 over pyridine. So what you would write is you would just write SOCl2 pyridine. Now what this does is it turns a carboxylic acid into what's called an acid chloride. So all it is we have this OH, and it does this. Replace that OH with a chlorine. These guys are super reactive, all right, this right here. So this can be pretty useful. So what I'm going to do is I'm just going to jump off the structure we created here. SOCl2 pyridine, and we get this product. Oh. This is our product. All right, it could be super, super useful. Why do I say it could be useful? Well, what I could do is, if you guys remember your Frito-Crafts reactions, right? We react this sort of structure, chlorine, R group, for AlCl3, and what it does is it sort of attaches this to benzene, right? Kind of wipe away the chlorine. Here's your O and here's your R. Now, what I did here is I essentially made an intramolecular version, right? So now on a synthesis, what I could do is I could write just AlCl3, just this over an arrow, and it's going to take this to be your Frito-Crafts part, right? And so what we could do is we could create this cool looking ring. So here's my benzene, and now what I want to do is count the carbons to be safe. 1, 2, 3, 4. All right, and what you're going to get is you're going to get this. 1, 2, 3. Oh, my bad. Trying to make it a little bit easier to see. 3, 4, and bound to this guy. And on carbon 4, we had a carbonyl. And so when we had this 4 carbons right here, we created this 1, 2, 3, 4, 5, a 5-member ring. And so if I just wanted to draw that a little bit better to see, I always say draw the ugly thing when you're doing the intramolecular because it can help you see it a little bit easier. You get this. All right, and again, just a good idea. Always count to make sure. 1, 2, 3. Oh, and I messed up. So it's actually going to be 1, 2, 3, 4, 5, 6-member ring. Because remember, it's sharing a side. So you're going to have carbonyl, carbonyl, and that's going to be right here. 1, 2, 3, 4. All right, so we can create these cool intramolecular Frito-Crafts essentially. All right, and so you guys should definitely know this reaction because it could come back and be in handy. All right, so this was similar to the synthesis problem that was given on an exam, and use this 4-membered ring, this 4-membered anhydride. All right, and what we could have even done is we could have, before we did the Frito-Crafts with the AlCl3, I could have done something like, remember this guy, the zinc reduction with mercury and HCl, and got rid of the carbonyl. Right, now we'd have only this guy. Then gone to this step, SOCl2 over pyridine, and we'd have this, remember, without that carbonyl. And then our answer, our final answer, wouldn't have this carbonyl in it. It would just have this bottom one. All right, so you can see how this can come in handy for you guys, all right? And again, if we had some sort of substituents on it, like if the benzene had OCH3 or something like that, then it could definitely, the bonding of this could be different. Instead of bonding to this bottom carbon like we did, could have bound closer to the OCH3, all right? So I'd play around with this if I were you guys. Go to the CLC, get it checked over. The TAs are always there to help you guys, and watch out because it could be coming up in your exam. All right? Hope this video helped you guys.